take what we learned yesterday or what we reviewed yesterday about systems. And we're actually going to see today how systems works in every business that's ever survived. Systems are a huge piece of life. You may not see it right now, but once we kind of show you a couple of these examples, you go, oh, that makes sense. So three things we're going to do today then. The first one is to know how to graph a system of linear and absolute value inequalities of two variables. Yesterday, we did systems, but they weren't inequalities. They were just equations. Today we're going to do a system of inequalities. And then we're going to find the vertices of these inequality shaded region, and then we're going to figure out linear programming. How does this fit into real life? How do businesses use it? It's called linear programming. So those are our three objectives today. All right, well, let's start. Let's jump right into it. Let's start by graphing this system of inequalities. We have y is greater than negative 2x minus 5, and y is less than or equal to x plus 3. Well, we've graphed each of those individually. We just haven't graphed them together. We did in 1D. So let's just remember how to do this real quick. I'm going to do this one in blue first. Nicely, it's already set up as y equals mx plus b. So I'm going to go straight to negative 5. Okay. 1, 2, 3, 4, 5. And my slope is negative 2. Now, since I can't go down negative 2, remember the trick of you have negative 2 as a slope. That's the same as 2 over negative 1. Doesn't matter where you put the negative. So I'm going to go up 2 and then to the left 1. Up 2, left 1. Up 2. So there's my line. Down here. Again, accuracy is important, which is why I let you keep those little rulers. Because accuracy will be the day, word of the day as well. Then with this, wait, stop. But we need to, this is greater than, what should I have done to that line? Dashed it, yeah. So, dash it. And I want it greater than that, so which way do you think I would go? Up or down? I want greater. Up and to the right, right? We can test 0, 0. You see that it worked. Ooh, this one's in blue. And for you, when you do this, if you have any kind of map colors, or use the side of your pencil and shade it real lightly. Unfortunately, I can't shade, like this, but it's going to be even more important to shade because I'll show you why here. When we graph this next one, we want to use kind of a little different color. Keep them separate. So now I'm going to go to 3. 1, 2, 3. And my slope is 1. So 1, 1, 1, 1. And it's going to be a solid or dashed line. Solid. And make them long lines. Don't just go, or it'd be very confusing. We'll make them all the way through the graph. And which way am I going here if I want less than? If I go down or up? Down. So, when we were doing systems of just plain old equations, we looked to see where the two lines intersected. Or when you're doing systems of inequalities, what are you looking for? Yeah, where the shading interlaps, where the shading overlaps. So you have to kind of stand back and say, okay, so where is there green and blue? And at this point, get something out really dark and realize it's going to be from here to here. Here. With all this in here. And make that very obvious when you shade that this is the answer. And what do I mean by this is the answer? How many solutions are there to that system? A jillion trillion, right? And where are those points? Where they cross, where the shading intersects. Is this point over here, is that part of the solution set? No. Nope. Is this? No. Is this? No. No, this would make the blue one correct, but it wouldn't make this one correct. And this one would make the green one correct, but not the blue one. How about this one? Would it make either one of them correct? No, it's not either one of them. So, that's the idea. And I know you've seen it before, so we're going to run through this and get right to the application part. I want you to do one real quick. This first one is in standard form. And in standard form, sometimes remember we can do the old x and y intercepts by sticking zeros in. Pause this moment. There we go. So where do they intersect? They don't. And as I get up here, if we turn this equation into y equals an x plus b, you see that its slope is -2, and this guy is also -2. So that's scoop. So no solution on that one. All right. So I'm gonna claim you good there. Y'all do this if you feel okay with this. Okay, because we're gonna take it on to the next level. You'll be able to do that. This is just gonna have a line. Oh, we gotta do this. It's that's a little bit of a twist to it. What is this called? Y is less than 2. I always thought when there was one variable, you just did it on a number line. What's up with that? What's the context that it's given me though? The x and y graph. Hence, this is not a number line situation. So y is less than 2. I could write this as y is less than 0x plus 2. Oh yeah. And what's the slope of this 0? Or what has the slope of 0? What kind of line? Horizontal line. So I've got a horizontal line at 2. And it is going to be dash. And of course we will go less than that, so it's going to go down from here. That one's nice and neat. And then, wait, whoa, what kind of problem is that?
Absolute value.
An absolute value. So what shape is that baby going to be? Very good, thank you very much. And if there's anything other than a B, I'm going to cut your tongue. It's going to be a B. That's not gross. Okay, so how are we going to make this B? Well, we're going to look at our H and K. I don't have an H, I have an H, but I don't have a K, so I'm going to put 0. What's going to be the vertex of my V? 1. Opposite of HK, right? The opposite of H and exactly K. So 1, 0. Notice I'm putting that vertex in the middle of my quick little T-chart so that I can go in the middle and then go either side to get the 2 legs going. So I'm going to go to the left one, to the right one. If I stick a 0 in here, I get the absolute value of 1, which is 1. If I stick a 2 in here, I get the absolute value of 1, which is 1. So 0, 1, and 1, 0, and 2, 1. It's going to be solid lines. Alright, now let's do interesting. So let's test our 0, 0 and see which way on that V I should go. 0, 0 is out here. We'll test this guy. So 0, 0. So 0 used to be greater than or equal to 0 minus 1. 0 is greater than or equal to 1. That's just wrong. It's just wrong. 0 is not greater than or equal to 1. So that means 0, 0 is not part of the solution. So I'm going to shade inside the V. So the part they have in common is this little bitty right here. I'm going to shade that in nice and dark. Somehow be creative. Some kids like to use highlighters for this piece. But it's just that little bitty section. So there's still an infinite number of solutions that they are in that where those shaded areas come together. All right? Okay. We're going to call that good. Let's move on. This is a linear program. This is where inequalities come in. And the thing about linear programming is that every business does it. Because a linear program, what it does is it maximizes your profit. Maximizes your profit. Every company, the goal of every company, at least profit companies, not non-profits, the goal is to make money, right? If you lose money, then you're out of business. So the goal is to make money. So but you have some limits. You always have limits. They're called constraints. Is another word for limits. You have constraints, like you only have 20 employees. Well, then you can't open up $1 million facility and you've got 20 employees and have them all work 58 hours a day. That doesn't add up. There aren't 58 hours in a day, and it just doesn't make sense. You can't do that unless you have more than multiple. So you always have your constraints. You always have your constraints. And you always have your expenses. Because you got to pay for the electricity, you got to pay your salaries. So you've always got positive and negatives coming in. Any of y'all have taken, what do we have, personal finance, or do we have any kind of business, I don't know what we do. Business classes talk about, how to make profit and all that. Well, this is a mathematical model. And we're gonna take this first example. It's gonna be a real simple company. I mean, it's so simple that it's not even realistic, really. But I got to start simple so that then you realize that, oh, I can see how this could be expanded to big companies. And usually this is all programmed into their computer somehow. That's why most companies have some kind of computer person on staff, even if it's not a computer company, but especially these days. Because they've got to make sure that they keep everything straight. You take you see the stockers in hen house every once in a while, counting all the inventory, and they're putting that in a computer, and it's going into this big spreadsheet that some guy made. So this is a very simple way that works. All right, example. A potter wants to make and sell serving bowls and plates. A bowl uses 5 pounds of clay. A plate uses 4 pounds of clay. The potter has 40 pounds of clay and wants to make at least 4 bowls. So when you read this problem, you realize there's some constraints here. I'm going to let it be bowls, number of bowls, number of plates. One constraint is that 4 pounds of clay, the plate plus 5 pounds of clay, the bowl has to be less than or equal to the 40 pounds of clay he has. I know that his bowls have to be greater than or equal to 4, because he needs to have at least 4. And his plates, he could make some, he may not make some. So the plates have to be greater than or equal to 0. All right, then this is considered an objective function. What is your objective? What is your goal? The goal is to make your profit as big as possible. So they want this P here. I make $35 per bowl plus $30 per plate. And that will be my objective, to maximize profit. All right, so what we're going to do, we're going to graph our constraints on a graph. We're going to use a graph. We're going to graph our constraints, and we're going to shade where all those intersect. And that shaded region is going to be called the feasible region. It's going to give you a whole bunch of options. You know how I keep telling you that there's an infinite number of solutions inside that shaded area? So he has a lot of options. You can make 2 bowls, 1 plate. I mean, I'll show you all the options once we graph it. And so there's a lot of options that are feasible. But he doesn't want to do the ones that are feasible. He wants to do the one that will make him the most money, right? Yes. So he wants to maximize or minimize the value of the objective function. And this will occur at the vertices. You know what vertices are. It will occur at the vertices of the feasible region. Okay, let's do it, and then it'll make a lot more sense. All right, so here were our constraints. Remember, these were our bowls. I'm gonna leave the x's and y's to make more sense here. But we had the bowls were greater than or equal to 4. These were our plates, right? And this was our 5 bowls plus 4 plates had to be less than or equal to 2. So I'm gonna graph my three constraints. And it'll give me an area on my graph. So I want to go x is greater than or equal to 4. X is greater than or equal to 4. Now what kind of line will that be? Vertical line, right? The vertical line at 4. So I'm going to go vertical line at 4. So 1, 2, 3, 4. No, 1, 2, 3, 4. Vertical line at 4. And that needs to be greater than or equal to 4. So that will come out this way. Okay, then y has to be greater than or equal to 0. Well, plates have to be greater than or equal to 0. What kind of line is that? Horizontal where? It's 0, right? I could write this as y is greater than or equal to 0 at 0. So I've got a horizontal line here. It has to be greater than or equal to that. And then this one, let's do a in standard form, and these two numbers are factors of 40. Let's do a little XY chart, sticking 0 for x and 0 for y. So let's stick a 0 in for x. What will y be? And if I stick a 0 in for y, what is x? Everybody follow me? All right, so let's graph that. So 0, 10 is here, and 8, 0 is here. That line is going to go this way. And we're going to shade less than or equal to that, so that's going to come down. So do you see where they all three come together? They all three come together in this triangle. Accuracy is important here. In this triangle right here is where all three of those come together. So I'm going to erase everything else except for that triangle, because that is our feasible region. That's what I can do with the amount of clay I have and my constraints about my bowls. This is my feasible region, which means any point in here will work. So this point right here, that would be 1, 2, 3, 4, 5, 1. That would be 5, 1. So that would be, what did we say, we made our x, our bowls. So he can make 5 bowls and 1 plate. Or this point would be in there. That's the point 1, 2, 3, 4, 5. 1, 2, 3. You can also make 5 bowls and 3 plates. So there's a lot of options that he has. But he wants the one that's going to maximize his profit. And maximization will happen at your vertices. Remember how I said that? So you're going to look at your vertices right here, here, and here. Accuracy is important. So let's see, where are those vertices? Well, this vertex is at 1, 2, 3, 4. This vertex is at 4, 0. This vertex is at 1, 2, 3, 4, 5, 6, 7. Woo! Is that an 8? Yeah. Is at 8, 0. And this one is at 4, 1, 2, 3, 4, 5. So one of those 3 combinations there are going to maximize his profit. So where you're going to put those 3 points is in, remember that objective statement that he had? That's where we're going to put in all 3 of these points and see which one gives him the biggest profit. So we're going to take those 3 points. I did find the 3 of them in the next step. So here's the 3 points we found. And this was the profit statement, the objective function. Remember, he made $35 per bowl plus $30 per plate. So I'm going to take those three vertices, plug them into that profit statement, and see which one gives me the biggest number. All right, so if I put 4 in here, this profit would be 35 times 4 plus 30 times 5. This profit would give him, let me calculate on this. I'll grab mine to do those numbers there. And we're looking for money that would bring in for him. 35 times 4, 140. Plus 150. We got 290. This combination, doing 4 bowls and no plates, let's see what that does for him. So that'd be 35 times 4 plus 30 times 0. Now, that's not going to be too hot. That's just going to be, what, 140. And that's not bringing in a lot. How about 80? So 35 times 8 plus 30 times 0. 35 times 8 is 280. Ooh, that's close. So these two are very, very close. He's going to make $10 more, though, doing that one. So this is what he's going to shoot for right here. He's going to tell his company, okay, guys, I figured this out once mathematically. Now I know that my company is going to make 4 bowls and 5 plates a day. So get busy, potters. Start wheeling those out. Okay, so you can see how you put this on a big scale, and I mean, huge computer program on how to get that to work. So we're just going to take little bitty bite-sized things. All right. Okay, questions? So we set up our constraints first, then we graph those constraints, find the shaded area, find the vertices, and then put those vertices into your profit statement or your objective statement. Okay, that's the steps. Wait, I got something under here. What is this? I'll put something in there. What is under there? I'm just curious. Oh. Just the questions we just answered. Which vertex maximizes profit? How many bowls and plates? Yeah. Yeah, we said all that. Yeah. Okay. All right. Here's another example. I'd like for you to do this one on your own this time. And what I've given you here, I'm not giving you the whole business model. I'm just giving you the constraints and what somebody's come up with. So here is your profit function statement that you're shooting for. Here are your objective, or your constraints, excuse me. So let's graph it and see what the heck come up with. And I'll walk around and look it out. Okay, where is my, As long as you get the idea here of where those points are, like I said, this is way up here, GA35. So we have those four, you see the idea, that's the feasible region, we've got the 4 points, tested the 4 points, stuck them all in our objective statement and objective function. And it looks like this right here would be the best way to make profit on this, to make 6 of whatever this is. And you're making, it can be shoes, it can be CDs, who knows what it is, and then 5 of that other product, and maximize your profit. Okay, I think the best thing would let me get you going. Well, shoot, let's go on and get the assignments, and we have that one there. I'm just not going to do that. So look at these here. I'm going to give you graph paper again because we'll do 4 graphs for this top one. 1, 2, 3, 4. This is not per graph, but we'll do 4 graphs for that. And this bottom section is 3 graphs for 4 and 5. And on 7 and 8, they're word problems. But all you need to do is find the constraints. You don't need to do the whole linear program thing. Just find the right constraints at number 7 and 8.